Alright, welcome to the multi-layer perceptron tutorial. I recommend watching this YouTube link over here video by 3 Brown 1 Blue, which is very useful, and I'm going to use a figure from them. And I'm going to upload this video, so you can check it out. And I'm using here 3 sort of tutorials, which is toy examples, which is always a good way to start. So we talked about the perceptron and how it's a sort of a gateway that holds numbers between 0 and 1, and based on those, is turned on or off, or fires, or doesn't fire. And so here, just a very basic Python code to show how when we connect the perceptrons to a layer, we can use several of those layers to get a very accurate prediction. So once we use a large amount of those layers, we get what is called deep learning. Cool. So this super easy code is just to get us started, and then I want to discuss shortly what is feed-forward, and I'm going to end with a bit more complicated version of the code you can play with. So this is just a nice code. I found this guy from Oxford that just plots the network. And so, for example, if we start from the bottom here, then we go through layers that can be of a different dimension from the input or the output, and then we arrive at some output. So dimensionality changes. And for our example, I'm going to use this. And now the question is, what is the mapping? What's the function between inputs and output? And it's not too complicated, so pause the video for a couple of seconds and figure out what over here predicts the output. So I'm assuming you pause the video and you figure out that the leftmost column over here is the predictor. Is as simple as that, but for our machine to learn this, it's not such an easy task. It's pretty cool. So this trust guy is made very useful to example over here. So we're going to use the sigma function, its derivative that we've discussed. Of course, we can use any other activation function. And by now you should all know what's this, and what's this, and I'm not going to tell you because, of course, you know it. And so we use output, which is, as you can see, different from what we've got over here. This input, but not too different, right? So as we said, our predictor is going to be the leftmost column. So we should expect 0, 0, 1, 1. So our output data set is, unsurprisingly, 0, 0, 1, 1, right? Once it becomes like this transpose should become a column. And I'm going to set it so we can run the code again, and whenever we generate something random, it's going to be generated in the same way, such that we can debug the code. And this is useful because when we initialize weights, as said in another video, it's many times done randomly, right? Like it's done over here. So the initialization of the weights over here for synapses, basically the first synapses, which is connection between the 0th or the first layer and the second one, is done in this way. So generates sort of a number in this formula. It's gonna actually, this is just tailored for the specific problem. So of course the convergence is gonna be better as the initialization is closer to the reality. And then we're gonna go into the actual training and learning. And so what we're gonna do is something called forward propagation. And I'm gonna stop for a minute and go into this really cool slide generated by 3 Blue 1 Brown, which is the creator of the video we watched before this. And we're just going to zoom in into how the learning is actually done. And this is very important. So it's very important to understand the following couple of seconds. So our activation function takes as an input 3 things. So let's start from here, the bias, as I said. Something like the intercept for regression method, it corrects or it offsets our prediction. And then we have a matrix of weights. So the weights that are assigned to each input over here that we can just put in this matrix, and the input, the data itself, right over here. So this is a dot product. This is just matrix multiplication. So I'm going to take this line, I'm going to dot it, multiply it by our vector over here. We're going to do the number, and we can add a bias term to this number, and that's going to be a 1 unit generated on 1 data point, and or actually by several data points. So now that we've understood the math that goes behind this, so we understand that we're going to sum the addition of, or the output of the bias term plus the dot product of the input data and the weights. And the sum of this is going to go into our gateway, which is the activation function, which is the sigmoid in this case. So let's see if it's actually existed in the code. So if you can tell without keep looking in the video, then it's great. But if not, that's also okay. So X is our data, right? Right here. So it's sort of like layer 0. It's not really like a layer that influenced by anything before. it's like our sort of a priori. And then our first layer is going to be non-name, which is the activation function sigmoid, and it takes the dot product of this, which is the data, and the first synopsis, which is the weights, right? So synopsis is weights. It's interchangeable for us. Dot product of those. So you might be asking, well, here are the weights, here's the input data, or X, where's the bias? Great question. So this code doesn't take into consideration bias because it's just very simple. So that's what we do, right? So we essentially have this one layer. Let's just start with one layer. And we can calculate the error. So the error for this layer is Y, right? The output data set. So this is labeled, right? Minus what we achieved during the learning. So very simple. And we're going to take this error, right? How much we missed. This is the modified error. And we're going to multiply it, and this is an important aspect, by the slope of the sigmoid, or in other words, blank. And I guess you thought about the derivative, right? So the delta, or the quantified miss, is the error times the derivative of the activation function. Taking the layer we calculate the error for as an input. And what's that? Well, that just says that we're going to take the derivative. That's true. We're going to take the derivative. We're going to use it instead of the function itself, right? So this is how we achieve the delta. And once this is done, we want to update the weights for the next layer. So assuming we go to the next layer, if we have a multi-layer perceptron, so our synopsis is going to be updated by the dot product. So generally, as you might have guessed, dot product kind of tries to point at some similarity or integration of different components. So we're going to take the data, or actually the transpose of the data, and we're going to take the delta, and we're going to multiply them, and we're going to get updated weights. So taking the transpose of the data, or right here, and multiply it by what we learned that we missed, and we're just going to print our prediction, basically, right? So this is just sort of one layer prediction. And we get almost 0, almost 0, almost 1, almost 1. So not too bad, not too bad. Almost 0, almost 0, 0, 0, 1, 1. Nice. So I feel like we're ready to proceed to something a bit more complicated. So here we basically just define relevant classes. We generate layers. So you will see this is very similar, right? Synaptic weights, right? So we said these are just weights. It's actually a very similar formula, and we generate a network by using the layers. We have our sigmoid, we have our derivative. You can go through the code slower, with the video in slower pace. And our training is iteration. Number of iterations is very, very similar. And we're going to take the output from the layer, and we're going to get it from think. So what is think? Let's see. So think takes, firstly, it gets the output from layer 1 and the output from layer 2, and it returns those by using the sigmoid. And we all know now that what the sigmoid is going to take is a dot product of the data, here called inputs, right? And the relevant layer, the relevant weights, right? Or the synapses or the synaptic weights, you choose. And here we're going to have the same thing, because the input of the second layer is the output of the first one. So it makes perfect sense. So here we have 2 layers, and this can go as up to n, whatever number of layers you want. We're going to return those. So this is not the super generalizable code, but it's very straightforward, so it's great for us. So we went to think with the training set inputs. So we understand that this training set inputs must contain the inputs that can be used for the first layer, that can be the dot product with the weights that were randomly generated, so we can achieve the desired weights for the second layer with the output from the first layer, and take these 2 back and assign those to the outputs from the layers, calculate the error like we've done, which is the difference between the desired output and what we got from the relevant layer, and we're going to get the delta. And now, if you remember, we used the derivative, which was called in some other name. It starts with g, and we're going to multiply the 2, and the same, and we're going to adjust the weights. And so we're going to first calculate how much we need to adjust the weights. So it's going to be the transpose of the inputs um, with the delta. Okay, so we're going to eventually print how well we've done in our progress. And the main function just basically triggers everything. There's nothing special over here. So, well, actually, I can run it if you want a proof. This is super robust. So we started randomly and we went through the layers. So we see our layers, right? And we see the weights, because we said the weights is the knowledge that we get, essentially. So this is after some training, right? Consider a new situation. So this is going to be the input. So our results. So consider a new situation. So let's just understand what we predicted and what was the data. And so the input looks like this. So it's a sort of a matrix, right? We all know a matrix looks like this. And we've got, oh, this is a flattened matrix. And I'm going to tell you that there's a bit of a hack. So the learning or the mapping function is ignoring the third column, right? And then using the exclusive OR with the two leftmost columns. This is a classic sort of a neural nets tutorial go-to example. And it says either the first or the second one is 1, then we're going to get a 1 in our output. So is 0 or 0, 1? No. Is 0, 1, 1? Yes. 0, 1, 1? Yes. 0, 1, 1, 0? Yes. 1, 1. So it's exclusive OR. So if the 2 are 1, then you get 0. If the 2 is 0, then you get 0. And so what if we get 1 and 0? We predict 0, and indeed we get something very, very close to 0. Well done, neural network. So we get 1 and 0, spits out 0. There are very useful resources right over here. Some useful demos. Card Party is master of machine learning. He wrote about understanding those concepts without math. Pretty useful. So I hope you find it useful, and you're welcome to comment and get in touch.